It all begins from a single origin, a unique point in space and time. This is the spark of innovation, fueling your most amazing breakthroughs with the power of AI. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, deep learning is helping farmers feed the world, and marine biologists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and deliver relief to those who need it most, even under the harshest conditions. We see robots teach themselves to perform simple tasks. We even watch as they tap into the power of deep learning to separate trash from treasure. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. GPU deep learning is the breakthrough that sparked this AI revolution and fuels your most amazing discoveries yet to come.
Ladies and gentlemen, please welcome NVIDIA Vice President of Developer Programs, Greg Estes.
Welcome to our first GTC here in the nation's capital. We're very excited to be here, and I think it's quite an appropriate time to have a dialogue about what's happening in deep learning and artificial intelligence. Many of you know that the White House has released 2 reports recently talking about where the future of AI is going for the nation and where we need to make investments and the things that we need to be considered, and what a perfect place to do that here with such a stellar group. GTC is, at its heart, our developer conference, and it's a little bit more than that as well. Certainly, we have more than 1,000 of you that have registered to come today, and we're very grateful for that. And it's from lots of different parts of the industry, many different government agencies, quite a number, a couple of dozen universities and research centers. Some of the largest and most important members of industry, big companies, but also startups as well. So we've got a pretty good smattering across a lot of different areas that are going to give you a chance to learn from the cutting edge of what's being done and have a dialogue with your peers. Both for developers, as I said, and also for those of you that are more interested in the business side and where policy is going. So we have something for everybody. We have, as you can see on the slide there, quite a number of technical sessions, and you're going to hear from just a stellar list of speakers, starting with the keynotes this morning, which we are humbly grateful to have attracted such high-profile people to come here and talk and have a dialogue with you around that, but also continuing through the 80 odd sessions that we have that are going to dive into not just artificial intelligence, but high-performance computing and virtual reality and a number of other things that are important to have discussions around it and learn about. We also have something that we call the Deep Learning Institute, and we have 22 hours of training that are available. So many of you in the audience here will be taking those classes, and that's been highly successful for us as a way to both have folks who want to just get started with deep learning and also some classes for those of you that have some expertise already and would like to go forward looking at object classification and image detection and looking at multiple different frameworks and a lot of different areas that are important areas of research and work that's being done and commercial applications today in deep learning. And all of this is made possible by our number of sponsors and exhibitors that we have. I think almost all of you have had a chance to see the exhibits out there on your way in today, and there's some things that you will be able to see here that you maybe have never seen before. We do a lot of work to make sure that we're bringing some cutting-edge things. We'll have a few demos for you here as well, and I hope you'll enjoy it. This has been the 7th, I guess, of our beginning to take our GTC conference, the GPU Technology Conference, worldwide. And we're almost at the end of the tour, and it's been very, very successful for us. And as a matter of fact, the growth that we've seen there from the number of developers that we've had just a few years ago to, the slide says 16,000, but now even here we're more than 17,000 people that have come to this set of conferences over the last 5 or 6 weeks, and then we're also going to go to India as well. So it's indicative of the amount of interest that we have in GPU development in general, but particularly in deep learning, and particularly in AI. And this growth is not just at GTC. We have also had, as part of our developer program, a huge growth that we've seen with about 400,000 registered developers now that are part of NVIDIA's developer program, which gives them access to the NVIDIA SDK, which has about 100 different SDKs of all kinds. Deep learning certainly, but also things like virtual reality and dealing with video and even gaming and some things like that, so across a wide range. But the particular growth that you see, just an astounding thing, is the number of deep learning developers. Look at that number, 25 times in just a couple of years, the number of deep learning developers that we're seeing as part of our program. And if you look at the list there, you'll see higher ed and the research centers at the top of the list, but you also see that it spreads out across quite a number of different industries, not in any, just one particular place, but a wide range. And that shows you that we are really at the beginning of a revolution, the GPU deep learning revolution and the AI becoming part of our national discussion, and certainly in every facet of computing now. So maybe the question is, why NVIDIA and why now? Well, we've really become the AI computing company. Those of you that follow NVIDIA at all may have seen us pivot very quickly and focus our attention very strongly on deep learning and AI. But we do have a history that leads us to this spot. If you think about it, we've been in supercomputing and simulation for a long time. As a matter of fact, some of you might know that our nation's largest supercomputer features our GPUs and is accelerated by our GPUs. Doing simulation for things like high-energy particle physics or new sources of energy and quite, the wide range of things that one uses supercomputing for. And then historically, for more than 2 decades, we've been in the graphics business, and some might say that we're simulating your imagination, because often the people that are using our GPUs are in the design area or in visual effects, et cetera. For instance, I can say with some confidence that the car that you drive was designed using our GPUs. We have about 100% market share in that part of the market, and certainly for visual effects. Every movie that you've seen over the last 10 or more years, all of the visual effects have been done with our Quadro graphics. And so these artists and designers have an image in their mind of what they're trying to create, and we're simulating that reality. So we simulate the physical world with our compute capabilities, and we're simulating your imagination with our graphics capabilities and bringing that vision to life. And now we're simulating intelligence. And that's what this conference is all about, this movement into AI and deep learning. And so to tell you more about that, we've got our list of keynote speakers, and I want to tell you about the first speaker now, Dr. Bill Dally. Bill Dally joined NVIDIA in January 2009 as chief scientist after spending 12 years at Stanford University, where he was chairman of the computer science department. Dally and his Stanford team developed the system architecture, network architecture, signaling, routing, and synchronization technology that is found in most large parallel computers today. Dally was previously at the Massachusetts Institute of Technology from '86 to '97, where he and his team built the J machine and the M machine, experimental parallel computer systems that pioneered the separation of mechanism from programming models and demonstrated very low overhead synchronization and communication mechanisms. From 1983 to 1986, he was at the California Institute of Technology, Caltech in other words, where he designed the MOSM simulation engine and the Torus routing chip, which pioneered wormhole routing and virtual channel flow control. He's a member of the National Academy of Engineering, a fellow of the American Academy of Arts and Sciences, a fellow of the IEEE and the ACM, and he has received the IEEE Seymour Cray Award and the ACM Morris Wilks Award. He's published over 200 papers, holds over 50 issued patents, and is an author of 2 textbooks. Dally received a bachelor's degree in electrical engineering from Virginia Tech, a master's in electrical engineering from Stanford University, and a PhD in computer science from Caltech. He is co-founder of Velio Communications and Stream Processors. All of that says Dr. Dally knows what he's talking about. Please help me welcome him.
Well, thanks, Greg. It's a real pleasure to be here. I'd like to thank all of you for taking time out of your busy schedules to come and be a part of this GTC. But I think you'll find it worthwhile because I personally find this one of the most exciting times to be part of GPU computing. First of all, let me say we're celebrating an anniversary. It was 10 years ago in 2006 that we launched GPU computing by launching CUDA. There's actually a history before that where a lot of the sort of predecessors of GPU computing were developed in a project at Stanford University called Stream Processing. Ian Buck, who's the general manager of our Tesla business unit, was a graduate student on that project and developed some of the first stream programming languages, something called Brook, which ultimately, from the learnings of that, he went on and developed CUDA at NVIDIA. And over these past 10 years, we've seen GPU computing enable enormous number of both wonderful science. The first atomic model of the HIV capsid, which allows us to both understand how it invades the cell and also to be able to predict computationally how different medications will interact with it, and allows us to develop better medications more quickly, as well as a 3D model of the human genome. But in many ways, probably the most significant advance of GPU computing over the last decade has been that it has enabled deep learning, starting with computers being able to beat humans at the ImageNet competition, not just an average human, the expert human who curates the images. The GPUs now beat them at being able to say what a particular image is, to being able to beat the world master at the game of Go. But before I dive into deep learning, let me talk a little bit about how GPUs enable science. Greg talked about the fastest computer in the US. Turns out also the fastest computer in the world is powered by NVIDIA GPUs. The bulk of the floating point operations in this Titan machine at Oak Ridge National Laboratories is provided by our GPUs and really fuels a lot of science today. And we're going to go beyond this. Next year, in collaboration with IBM, Our GPUs will be providing the bulk of the floating point operations in 2 supercomputers, one at Oak Ridge National Laboratories and one at Lawrence Livermore, that will be the fastest machines in the US at that point in time and will fuel a great deal of new science. And we see, we call these pre-exascale machines because we see them as one step on the way to building an exascale computer. We've been working actually for more than a decade with the Department of Energy on research leading to an exascale machine. There are many challenging problems to be solved to get to exascale. One is to do it at a reasonable power level, and that is in many ways a proxy for affordability. We have to get dramatic increases in the efficiency and the flops per watt of our computers. We're doing this in an environment where Moore's law is really over. We're not getting anything out of process anymore. The advances we're getting in performance per watt is coming almost entirely from our cleverness and coming up with better architectures and circuit technologies. We also have to develop a number of new programming technologies to make it possible to program these machines without heroic effort. And we have a big effort on at NVIDIA with something we call target-independent programming, where we try to get the programmer to operate at a higher level, specifying what the algorithms are, all of the parallelism available, and an abstract notion of locality, and then letting machines do what machines are good at and computing the optimal mapping of that abstract programming representation to the hardware. And this allows you to move from one piece of hardware to another without having to spend hundreds of person years recoding, which is what's done today. So what this enables is in a broad range of science, press the button and nothing happened. In a broad range of science, the instrument today is a supercomputer, whether it's running models of our Earth and atmosphere, both to predict the weather and to understand the effects of climate change, whether it's simulating new, more efficient forms of combustion engines, that's on the upper right, to reduce the amount of carbon we put in the atmosphere and slow climate change, whether it's simulating the collision of galaxies to better understand the formation of the universe, whether it's simulating biological systems to improve our understanding of biology and to improve our healthcare. The way people accomplish science today is very much on computers. There was a point in time where if you wanted to do great science, you built a big telescope, and the person with the biggest telescope made the best astronomical discoveries. There was another point in time where people built great particle colliders, and the people who discovered the next subatomic particle were the people with the largest and highest energy particle colliders. Today, the people who make the biggest strides forward in science are the people with the biggest supercomputers. It's very much the case that the supercomputer is a scientific instrument of the 21st century. So let's move from having GPUs fueling discovery of science to deep learning. What's really driving the need for deep learning is the fact that we live in an era of big data. Nowhere is this more prevalent than in the cloud, but it's actually true all around us with the Internet of Things, with many things. We're collecting an enormous amount of data today. There's over 3 exabytes of web content created daily. There's 350 million images uploaded just to Facebook every day and many to other cloud service providers as well. And over 400 hours of YouTube videos uploaded every minute. So there's enormous treasure trove of data on the web. And the question is, how do we make sense of it? How do we organize it? How do we find something we're looking for, understand it, and benefit from this enormous amount of data? And the answer is deep learning. The interesting thing about deep learning is all of the pieces were around. All of the algorithms that are used today, with a few small exceptions, have been around since the 1980s. Convolutional neural networks were developed by Jan LeCun in the 1980s. Stochastic gradient descent and backpropagation, the methods used to train these networks, were around in the 1980s. The large volumes of data that you need to train the networks have been around since about the middle 2000s. But it wasn't until 2012 that deep learning really started to be applied in a meaningful way to solving problems. And what was causing this was a missing ingredient. You can think of the techniques, the convolutional networks and the methods for training them as kind of being the air and the huge amount of data as the fuel, but we were missing a spark. And that spark was adequate computing to train the models. So it wasn't until 2012 when GPUs were applied to train neural networks that they began actually to be useful. It was the missing ingredient. And once it took place, it's actually been a lot of fun to watch what's happened. It's literally spread like wildfire. So in 2011, I kicked this process off at NVIDIA by starting a collaboration with Andrew Ng at Stanford University, where we took a network that Andrew had been working on at Google. You probably read about this in the New York Times and other places. This was the network that found cats on the internet. But to find cats on the internet, Andrew had to use 16,000 CPUs at Google. And I was actually having breakfast with him one day, and he's kind of lamented to me that this was not accessible, that the average researcher in a university didn't have 16,000 CPUs. And so I suggested to him that he run this on GPUs, and then actually got some resources, both GPUs and a scientist from NVIDIA Research to work with him on the project. And he was able to replicate that experiment of finding cats on the internet on 48 GPUs. And this really democratized deep learning, because no longer did you have to have huge resources to find cats on the internet, or to do image recognition, or to do speech understanding. Average academic researchers could, with a reasonable budget, equip a small machine with a few to a few tens of GPUs and do cutting-edge research on deep learning. And it really took off from there. The middle panel here shows performance on the ImageNet competition. This is a competition of image understanding that's run every year by Fei-Fei Li at Stanford University, where you train on a corpus of 1 million images, 1.2 million images, and then you basically get a small training set, and you're graded on how well you understand those images. And the black line shows how well people did with traditional computer vision techniques. Up until 2011, the competition was won by people doing manually designed feature detectors. In fact, academics in computer vision spent their careers designing feature detectors with names like Hog and Sift, and that was the way you did computer vision up until 4 or 5 years ago. But in 2012, for the first time, deep networks trained with GPUs were applied to the ImageNet competition, and they won not by a small amount. The increase in that 1 year in the capability of these networks, in the recognition rate, was more than all of the increases in the previous 5 years. And then it took off from there, and the green line shows the improvement over subsequent years, all using deep learning, all trained on NVIDIA GPUs. And in just the last couple of years, it's surpassed the little dotted line across the top, human-level performance on these recognition tasks. And again, it's not an average human. That's actually the performance of Andre Karpathy, who's the person who curates the data set for ImageNet. In fact, it's a huge problem at this point that it's difficult to make sure that the ground truth is accurate, because the networks are now better than the people who are labeling the image and are calling the ground truth. And so there's actually an elaborate protocol with many people involved to make sure that what is called the ground truth is actually right. The panel on the right shows the application to speech understanding. And we now have better than human level speech understanding out of these networks as well. Again, fueled by deep neural networks trained on GPUs. So in many ways, this is another era of computing. Keep pressing this button, nothing happens. You can think of the 70s as being a mainframe era, and the 80s as being a mini computer era where everybody had a VAX. In the 90s, we had PCs and the internet, which sort of enabled all sorts of e-commerce and many other things. When the iPhone came out in 2006, we had the era of mobile and cloud computing. And now, especially every decade, we have an era. We are now entering the era of AI and deep learning. Intelligent devices are going to be the dominant computing force, and it's pervasive. To give you an idea how pervasive it is, this is a chart that Jeff Dean at Google showed earlier this year of the number of unique projects at Google that use deep learning. And you can see, starting off with just a few experimental projects in 2012 at the left side of this graph, with maybe a few more the following year in 2013. In the last couple of years, it's completely taken off. It's been an exponential growth where it's been applied to all sorts of things. You think of some of these, for example, the speech recognition has gotten a lot better. It used to be when you talk to your phone, it mostly got it wrong. Now when you talk to your phone, it mostly gets it right. That's better neural networks trained on NVIDIA GPUs to basically, when you upload images, it will now automatically tag the images with what's in them by having image understanding. But it goes across the board in almost every project they have now uses deep learning, and it's true in other industries as well. Deep learning is really everywhere. Whether you're in sort of a traditional scientific field, or whether you are in retail or a restaurant industry, people are using deep learning to make their businesses better. So in internet and cloud applications, it's things like image classification and speech understanding. Deep learning has the potential and is already transforming medicine and biology. In many cases, deep neural networks are exceeding the capability of expert radiologists in reading x-rays and reading mammograms and diagnosing disease. They're capable of basically looking at huge piles of data relating genotype to phenotype and understanding better how to prescribe drugs right the first time, rather than having to give the conservative dose and then titrate up slowly because people don't yet understand what an individual's response is to a particular drug. And they're able to mine huge amounts of data on symptoms shown and treatments given and what the outcomes were to better inform physicians on how to practice their medicine. It's transforming media and entertainment. We actually use it in graphics. We're starting to build deep learning into many of our SDKs for graphics to better filter images and for better content creation. One great application is what's called face rigging. If you have an animated character, you typically have a human character act out the scene and then animate that character. But there's a huge amount of artist labor involved in moving what's called the rig, very often sort of 300 controls that make small differences in expression on the face of the animated character. We can now greatly reduce that amount of human labor by an order of magnitude by using deep learning to learn the correspondence between the actor and what the rig should be doing. Numerous applications in security and defense, looking at images, but also looking at almost any data stream you have. Deep networks are great at identifying anomalies. You can train them at what is normal, and then they will find what is abnormal, even if they've never seen it before. And then one thing that we're most excited about at NVIDIA is using deep learning in autonomous vehicles. It's truly transforming how transportation will ultimately work in this country and in the world, and perhaps will put a dent in the 1.2 million people we kill on the roads every year worldwide. The fact that it's clear that deep learning is not a passing fad is that what the convincing evidence of that is it's exceeded human capability at many tasks, ranging from speech recognition, image classification and detection. That classification is saying what is it in an image, and detection is finding a particular thing in an image and locating it. Face recognition, it will see faces and will be better at saying who they are than a human trained on the same set of faces. Playing Atari games, which was the original sort of training ground for the techniques that were developed for reinforcement learning that were ultimately then applied to playing Go and winning at it. It's also the case that there's a synergy between our use of GPUs in science and our use of GPUs in deep learning, and that deep learning is fueling science. A lot of science involves large data sets, whether it's satellite images of vegetation where you're trying to understand the effect of climate change on forests that's done at NASA Ames, or whether it's looking at medical records for children admitted to Children's Hospital to basically inform physicians based on huge data mining studies of histories of symptoms, treatments, and outcomes, how to better administer medicine, or whether it's looking at obituaries, again, data mining that stream to understand cancer. Deep learning even fuels science in more traditional ways. We think of sort of the bread and butter scientific computing as doing physical simulations of things like fluid dynamics. Usually these applications have two components. There's a component that simulates the constituent equations of a basic finite element or other sort of small piece of the simulation. And then there's a solver that takes all of that and computes a system-wide solution. And usually the small constituent equation is a model, and there's many ways of doing that model. One way is to train it on deep learning, and recently people have done fluid dynamic simulations where rather than taking the Navier-Stokes equations and the basic physics and chemistry of what's going on in an individual cell and doing that computation, which is very expensive, they trained a deep network to basically say with this set of elements in this cell, this pressure, this velocity, and these fluxes through the faces of the cell, here's what your output pressure for the next state is. And they got 3 orders of magnitude speed up with comparable accuracy on their simulation. So deep learning is basically impacting almost every aspect of human life, from scientific computation to medicine to autonomous driving. So let's talk a little bit about how deep learning works and what the computing model is. We like to think of the deep learning computing model as having 4 basic components. The first component is training. And training is truly a demanding computational task. And this is why, even though all of the techniques had been developed in the 1980s, deep learning didn't take off until that missing ingredient of adequate computation was available just a few years ago. To give you an idea of the complexity, an average model today, what it is you're training, requires anywhere between 1 billion and 100 billion floating point operations to do a single pass through it, basically to take one image and learn from that image. But to learn, we don't take one image. A typical training set today is typically hundreds of millions to billions of images. Even the ImageNet training set, which is 1.2 million images, the people who win at ImageNet don't stop there. They do what's called data augmentation, and they expand that data set to billions of images so they have a larger training set. So here we have something which takes tens of billions of operations. We're running billions of images through it. We're already up to about 10 to the 19th operations to do what's called one epoch of training, one pass through the entire data set. But these networks don't learn on one pass through the data set. It typically takes many hundreds to thousands of passes through the data set to learn. So you quickly wind up with anywhere between 10 to the 21 to 10 to the 24th floating point operations to train a network. And researchers and practitioners are practically limited to the networks that they can train in roughly 2 weeks. That seems to be the attention span of people doing deep learning. And of course, you don't train one network. You're experimenting. You're looking for the correct network. And so you'll train tens of networks, in some cases hundreds of networks, before you wind up with the one that gives you the best performance at the lowest energy cost. So training is a huge demand on computation, and GPUs have really enabled this training to take place by providing energy-efficient computation, orders of magnitude more efficient than the alternatives. The next thing is the models, and models are improving all the time, and it's one of these synergistic things where the size of the model is roughly comparable to the size of the data set that you train it on, because as you build a larger model, it has more what's called capacity. And if you take a model with too much capacity and you train it on a small data set, you'll get a phenomenon called overfitting. It will learn your training data very well, but it won't generalize well to data that it hasn't seen. On the other hand, if you have a very large data set and your model is too small, you won't have sufficient capacity, and your accuracy will be lower than if you have a larger model. So you have to fit the model to the data set. And as time goes on, the people who use these networks, whether it's for image understanding or for speech recognition, for driving cars, get larger data sets. That means they need larger models. The models today, the state-of-the-art models for image understanding are now over 100 layers deep. And so the number of operations is continuously going up, and people are developing better techniques and better structures for these models. The introduction of residual networks a few years ago made a jump forward in performance of these models, for example. So once I got all the computing and the models and I trained my model, I now need to deploy it, right? The reason I trained this model is I wanted it to do something useful, whether it was drive a car, translate speech from one language to another, look for anomalies. And I do this by deploying it. I can deploy it in one of two places. I can deploy it in a data center. And this is a natural place for deploying it if it's doing a data center application like translating speech on the web or doing image understanding for data that videos or still images you've uploaded to a cloud service provider. It's also the place to do inferencing for the Internet of Things, where your thing has actually connected to the internet, collected data locally, and uploaded it. In many applications, your smart thermostats, many Internet of Things applications with video cameras, the inference is actually done in the cloud. Things are piped up to the cloud. You do the inference there, send down the results of that inference. And so in the data center, we need huge computation as well, but we don't need to train on billions of examples and do it for thousands, hundreds to thousands of epochs. We need to do it once, but we need to do it once for a huge data stream that's coming in. It's still a computationally demanding task. And then we also do inference in devices themselves. And there are two reasons for doing this, or perhaps three reasons. The first is you may not be connected to the internet. If you have a device which doesn't have a connection up to the cloud, the inference has to be done in the device. The second is a real-time constraint. If I have a self-driving car, I need to make an inference on an image my forward-looking camera sees in 50 milliseconds. So if there's a baby carriage in that crosswalk, the car will put on its brakes. I don't have time to take that image, pipe it up to the cloud, make a decision, send back the command to hit the brakes. It's too late. And so if there's a real-time constraint, I have to do that inferencing locally because I can't afford the time to send it to a remote computation site. And then finally, in many cases, it's actually energetically cheaper to do the inferencing locally than it is to spend the energy on the communication bandwidth to send the raw data up to a data center. What's interesting is that GPU computing was the spark that enabled deep learning. Today, it's actually pacing deep learning, in that what people can do is before it was sort of whether they could do it at all was limited by computation. Now it's how much they can do is limited by the available computation. So to give you an example of this, in image recognition, doing the training for AlexNet, which was really the network that brought GPU computing to image understanding, took a certain amount of computation, and so let's see, it's 1.4 gigaflops to train the network and get 16% error. Moving over the past 3 years, or 3 years from 2012 to 2015, when Microsoft's ResNet came out, had 152 layers, used data augmentation to give a larger data set so that it wouldn't overfit on that. So, but with both that larger data set and the larger number of layers, it took 16 times as much effort to train that model. And it would have been 160 times, except there were improvements in technique going from AlexNet to ResNet that actually reduced the computational load. So improvements in technique mitigated that somewhat. But still, there's more than an order of magnitude increase in computational demand in just 3 years. In speech, it's even a larger change per year. Baidu, in going from Deep Speech 1 to Deep Speech 2, took 7,000 hours of data to 12,000, not quite doubling the amount of data. But to handle that larger amount of data on a network, the network went from 80 gigaflops to over 400 gigaflops, more than 5x increase. Twice the data, 5 times the flops on the network, and now they need, in 1 year, 10 times the performance. And in many ways, they're gated. They could collect larger data sets, but they're now limited because on the largest machines they can efficiently build, all they can train in 2 weeks is the Deep Speech 2 network, where they get faster GPUs, they'll build a deeper network, they'll get more data, and they'll get even better results on speech. So right now, we're pacing the rate of improvement in these networks because people are building the largest networks that they can train in roughly a 2-week period. And they're collecting larger data sets, but aren't able to sort of build the networks large enough to use them yet. So we've been working hard not to sort of get in the way of progress here. And our latest offering in this space is Pascal. Pascal is truly an amazing GPU. I've got one here. I'll hold it up when I get to the next slide that shows the close-up of it. But across the board, we're taking Pascal itself, which is got high bandwidth memory. It's got a technology we developed called NVLink to break the communication bottlenecks of building multi-GPU systems and to free the communication between GPU and CPU. We're offering it both as a single GPU, but also in a system called DGX1, which is 8 Pascals tied together. And with this set of technologies, going back to Kepler, which is what people used in 2012 for the original AlexNet on ImageNet, we have a 65 times performance improvement on training deep neural networks. And this is in an era where we're getting nothing from process technology. In fact, the first 2 points on this graph, Kepler and Maxwell, are in exactly the same semiconductor process. They're both done in a 28 nanometer process at TSMC. So the 10x performance improvement we got going from Kepler to Maxwell is due entirely to architecture and circuits. There's nothing, no benefit from process technology there. And then the 6.5x we get going from Maxwell to Pascal is almost entirely due to better architecture. We're getting perhaps maybe 20 or 30% performance improvement due to process technology there. So this is really because we got started with deep learning back in 2011 and realized that it was an important problem. We've been working for 5 years to understand how to make GPUs better at deep learning, to optimize them for training and deploying neural networks. And that's what's given these huge improvements in performance over the years. And also because we've been working on it for that long, we're integrated into all of the major frameworks that are used for training these networks. So let me talk a little bit about Pascal, because it's something that I'm personally very excited about. This is what's called an SXM module. It's a module, a daughter card that sits on a motherboard in a machine that uses Pascal. In the very middle here is the Pascal GPU. It is a large chip. It's nearly an inch on a side, to give you some perspective, almost 600 square millimeters. And around it are 4 stacks of memory. This is the 16 gigabytes of memory, are all right here in the center of this chip. Whenever I show this module, everybody thinks these are the memory chips. These are inductors. This is a 16-phase interleaved buck power supply that provides up to 400 amps of current at typically less than 1 volt to the Pascal GPU. And the really cool thing about Pascal is on the back, these are 2 connectors, and I'll have a picture shortly that shows them exposed. And because all of the memory is connected directly on this silicon interposer to the Pascal GPU, we don't need to have any of the 750 gigabytes per second of memory bandwidth go out through the connector. In fact, if we had to take it out that far, it energetically would be very inefficient. This would dissipate a lot more power. What's coming out the back here is NVLink, 160 gigabytes of bandwidth to talk to CPUs or other GPUs. And that really enables us to build powerful systems with more than one GPU and with CPUs and GPUs working in concert. So it's an amazing device. It's 10 teraflops of 32-bit floating point. But one thing we developed in our experimentation starting about 5 years ago is the ability to train neural networks using 16-bit floating point. If you just go out and naively try that, it actually won't work. Your networks won't converge. But if you properly scale things and apply certain normalization techniques, we've been able to train almost every network we've worked with 16-bit floating point. And so this is 20 teraflops of FP16, which really enables huge steps forward in training. Many applications of deep networks are memory bandwidth limited. You have a huge set of activations during the training process. You've got that activations times the number of layers, because you have to keep the activations for all the layers around until the backpropagation step. And then you have it with a large batch size, often a batch of 256 or so. So we often have gigabytes of data. It can't all reside on the chip. And the memory bandwidth becomes a limiting factor in training. With 750 gigabytes per second of HBM2 memory, there's nothing that even comes close to touching a Pascal in terms of its ability to handle that. The NVLink then allows us to scale things. And I'm very proud of this because it's a technology that came out of NVIDIA research and was very successfully transferred into product. On the backside of Pascal, you see we've got these connectors here that bring out these channels of NVLink, a total of 160 gigabytes per second worth of bandwidth. What it lets us do is take a bunch of these GPUs that have these 750 gigabyte per second connections to memory locally, and then tie them together as if they were one big GPU. And all you have to do is a load and store on one GPU, and you're reading from another GPU's memory. And so one example of this is DGX1, which is 8 of these Pascal GPUs tied together. So you can simply do loads and stores, basically a shared memory model, into the other GPU's memories. And it allows us to then scale our deep learning up to 8x. DGX1 also has a quad 100 gigabit InfiniBand connection coming out of it. So if you need to scale to even larger sizes, you can take a number of these DGX1s, connect them up with InfiniBand, and build a very powerful engine for deep learning training. So that is sort of the system that everybody wants. The other thing you can do with NVLink is connect up to a CPU. And we're working with a number of partners. One that's been announced is IBM on the Power 8 Plus has a NVLink on it. So you can connect a Pascal GPU to a Power 8 Plus CPU, and the Pascal GPU can use the entire memory bandwidth of that CPU. This is a huge step up. In the past, we had to connect to CPUs with PCI Express, which is a tiny little cocktail straw, not even a soda straw, that you're trying to slurp up all the data that's in the CPU memory with. And in a lot of these applications, we have 16 or 32 gigabytes of memory on the GPU side. You have hundreds of gigabytes of memory on the CPU side, and so you're moving things back and forth. With NVLink, you don't have to worry about where you put your data. NVLink, in combination with a technology that we have called UVM, which allows you to put your memory put your data in the CPU memory, and the GPU can just go out and get it with full bandwidth and not any real concern for where it was located. So that's sort of the hardware for training these networks. Let's talk a little bit about deploying them in the data center. After I've got the network trained, I want to run some inference in the data center. We offer Pascal packaged in a slightly different form factor. In fact, we offer two of them, P4 and P40. P40 is the 250-watt workhorse that's really designed when you have a lot of work to do and you want to do it most efficiently. P4 is a 50-watt version of Pascal. There's a little card here. And the reason why we offer the P4 is that many people have systems that don't have a PCIe slot with 250 watts or the height for the full module. So this will go into a 1U server if you have 50 watts in your PCIe slot, and is intended sort of for a legacy support. With either of these, you have a tremendous amount of computing capability. Another thing we found is that after you've trained these networks, you don't want to just sort of naively take them and play them back. There's the equivalent of compiler optimizations you can do to, for example, fuse different layers together and recognize common sub-expressions of operations that you're doing in these networks. And we have a software package called TensorRT, which takes these networks and often gives very substantial multiples of performance improvement. It's not unusual going from running the network directly in one of the frameworks like Caffe to running it optimized through TensorRT to get a factor of 3 or 4x performance improvement with no change in accuracy by running it there. So as an example of what you can do with one Pascal GPU, let me show you an example of a Pascal GPU simultaneously looking at 80 streams of 720p video. If we could flip to the demo, please. So we're going to bring these streams up sort of one at a time. They're 720p video streams. You're seeing only sort of a downsample of them here so that you can fit them on the screen. And they're basically videos of various activities playing back. One GPU is watching all of these videos simultaneously. And I can ask that GPU, what's going on? Please label these for me. Tell me what they are, right? So this is the GPU doing this by just watching the video. It's able to recognize the activity. And you and I would be good to sort of recognize one video and label it, maybe two. But I certainly can't watch 80 videos at a time. So this is an amazing capability. And then I can ask it to do some filtering for me. So show me just musical instruments. Okay. How about sports? A lot of sports. Let's narrow that. How about Olympic sports? What about gymnastics? Okay, let's put them all up there again. So, this is really an idea of what you can do with GPUs. That's a single Pascal, processing this in real time, 80 720p streams. Okay, let's go back to the presentation. Okay, so that's inference in the data center. Let's talk about the next part of our sort of ecosystem of deep learning technologies, which is inference in intelligent devices. So the Internet of Things is very excited. There are going to be billions of intelligent devices, cameras, audio devices. I don't know how many people have an Amazon Echo, but that's a deep network trained on NVIDIA GPUs, where you talk to your device and it does things for you. Drones, autonomous vehicles. For some of these, the deep learning the inference can be done in the cloud. For others, the inference has to be done in the device itself for either real-time constraints or lack of a connection. And for this Internet of Things, we offer both a hardware product and a software product. For the hardware product, we have our Tegra chip, which we package up in a form factor we call Jetson. It's sort of a Tegra chip with the peripherals you typically need, something about the size of a credit card. I should have had one of these to show. And it's an embedded AI supercomputer. It's the generation that is about to be phased out, our sort of Maxwell generation of Tegra, the TX1, is a teraflop of floating point 16 at 10 watts. We're just now starting to ship our Parker GPU, which is a significant step up from that. And this is basically the Raspberry Pi for building deep learning Internet of Things appliances. You basically take a Jetson, write a little bit of software. We've got SDKs with all the neural networks you're likely to need, and you can be in business. A particular application of this we're very excited about is transportation and autonomous driving. This is a $10 trillion industry if you look at cars and trucks and shuttles and other aspects. And it's also a place where we feel that we can do social good. We kill 12 million people on the roads worldwide through accidents that are avoidable because humans, quite frankly, aren't the best devices for controlling vehicles. It's amazing what we're able to do, but we get distracted, we get tired, we make mistakes, and people die as a result of that. So again, we offer both hardware and software for this. On the hardware side, we take that same Tegra chip, which is in Jetson, to be put into cameras and audio devices and other embedded systems or drones, and we package it up in a automotive supercomputer, which we call DrivePX2. And the DrivePX2s actually use our Parker generation, one beyond the TX1 that I showed before. And because it's not one size fits all, people have different needs for autonomy. This scales from our AutoCruise, which is a single Parker chip, about 1.5 teraflops, up to full autonomy, which is 20 teraops of deep learning inference, which includes 2 of the Parker chips and 2 discrete Pascal GPUs and a water-cooled supercomputer that can sit in the trunk of the car. So a zoom in on the low-end version of this, the single Parker is 10 watts passively cooled, 1.5 teraflops, and for a lot of autonomous driving, this is sufficient to run the entire package. And of course, NVIDIA being sort of a top to bottom deep learning company, we provide the entire package. We have a software package called Driveworks, internally developed at NVIDIA, that involves several key aspects of it. Let me see if the laser on this thing works. Oops, no, it just took me backwards. Okay, it's not a laser, it's a backwards button. Okay, let me just sort of point to some of the aspects here. So we actually have several different neural networks as part of Driveworks. One of them, DriveNet, is for object detection. It's looking out ahead of the car, and it's seeing where the other cars are, where bicycles are, where pedestrians are, where baby carriages are, finding these objects that are dynamically changing in the scene. For navigation of the car, we actually rely both on that, which finds lane markers and the like, but also on mapping and localization. We build very accurate maps of the world where these vehicles operate, and then we can start with a coarse localization of the car with GPS, and then using data from the imaging, locate the car to within millimeters on that map. And therefore, for parts of the scene that don't change, we can navigate the car very accurately, basically without looking. Once we've localized on the map, we know where the lanes are. The only reason you really need to do real-time processing is to find the things that are dynamically changing. And then we have another neural network which basically finds open space. It's this open road net. And open road net is basically looking at the scene ahead of you and identifying all the time where are safe escape corridors? How much space is ahead of the car? Is there anything to my left? Is there anything to my right? So if something should happen, the car immediately knows where it can jump. And one of the reasons why autonomous vehicles can be better than humans is they can look in all directions simultaneously. You don't have to turn your head when you're looking this way, you're not seeing what's happening there. They're looking in all directions simultaneously, seeing it all and integrating it. They never get distracted, never look away. They have complete situational awareness of what's going on. We have another neural network called PilotNet, which is actually a completely separate system, which also gives decisions into this. And PilotNet is actually trained by watching a human drive a car end to end. And so it's basically saying, in this situation, I think you should turn the wheel to the left, without actually breaking down the intermediate point of saying, here are the lane markers, and that's why you should turn to the left, or there's an obstacle there, and that's why you should turn to the left. All of this feeds into a decision-making process that predicts where the traffic is going, plans where you should go, and then actuates that. Now, I personally find PilotNet a really interesting aspect of this, because one of the bottlenecks with deep learning is getting labeled data. At NVIDIA, we actually run a fleet of cars. We send them out with video cameras on them. Drivers are assigned to drive different roads because we don't want to just get US 101 100 million times. We'd like to get different parts of highway. We bring that data back. We have a bunch of people who first curate the data. We don't want, again, we basically throw out data that would be too redundant with what we've already seen. And then we have an army of people who label that data. And this is actually the truly laborious process of deep learning, is getting labeled data sets. One thing which is really neat about the approach of our PilotNet is it doesn't take any labeling. We simply go out, we drive a car, the neural network watches what we do, and it learns from that. And then it can drive the car by itself in places that are different than what it's seen and make good decisions about it. So if we could roll the video on BB-8, this is actually kind of fun to watch the process.
Oh yeah, good. The universal sign for auto.
Yeah. So here's Urs Muller, who runs this part of NVIDIA, driving around in a car being driven by our GPU. The car was trained by just watching him drive, and at first it didn't do very well, so it would sort of run over the cones. It's sort of like training your teenager to drive. But after just a few sessions watching Urs drive the car, he can turn it over to fully automatic mode. And it will not only negotiate the cones, but it will drive on roads, both roads with lane markers, roads without, dirt roads, all roads it hasn't seen before. It can be a blind corner. It will sort of anticipate from the visual cues where the road goes. It'll turn around obstacles like those concrete posts.
So cool.
Places where it needs to make a sharp turn to avoid hitting a fence. Even places where there's construction and it has to go off the road. Go through these cones and then through a dirt area, the neural network will successfully navigate that. So it's amazing what can be done just training by watching. And in fact, to me, one of the very exciting fields of neural networks and AI is different techniques to basically be able to train these networks without huge labeled data sets. In addition to basically learning by watching, we have examples of reinforcement learning. This is how most of the game playing programs are trained, where they simply play against themselves and basically reinforce, give themselves a cookie when they win. And that cookie basically reinforces the neurons that made it win, and they get better over time to the point where they beat the human champion at Go. We also have places where we can get by without labeled data by using things called autoencoders that we use for a lot of image enhancement applications. So we're working with many auto manufacturers. One that's not up here but was announced recently is Tesla on this. These are the ones we're sort of allowed to talk about right now. Baidu, Autonomy, Volvo, TomTom, and WePods, taking this technology in our Drive PX2 hardware, our Driveworks software, and using it to enable these people to put autonomous vehicles on the road. Now, to make these systems even more powerful, we're sort of announcing the Tegra chip we're going to have available with our Volta technology, which is called Xavier. The Volta technology is what's going into those 2 supercomputers we're going to deliver next year to Oak Ridge and Livermore. That same sort of supercomputing heart goes in here. And what's amazing about it is the level of performance it gives. It's got a 512-core GPU and a number of accelerators to basically make some of these deep learning tasks go even faster. 7 billion transistors, truly an amazing embedded chip. And one way to think about it is today, to get the level of performance you get from a single Xavier on the right, it takes the largest Drive PX2 that we have, the one with 2 Parker chips and 2 discrete Pascals. And that gives you 20 teraops of deep learning performance at 80 watts, where this gives you 20 teraops of deep learning performance, even more CPU integer performance, and that's at 20 watts. So it's more than a 4x improvement in performance per watt in one generation and in the same process technology. Now, of course, we can't develop all the technology for deep learning ourselves, so a big part of what we're doing is collaborations. And what we've recently created NVIDIA AI Lab, NVAL, which is a collaboration with leading AI researchers at universities around the world. We've gone around, we've basically found the people who we think are the pioneers of AI technology, and we're working with them, collaborating, so that we can both accelerate the work they're doing and benefit and import into NVIDIA the better ideas that come out of those laboratories and get them into our products. And just to give you an example of one of these collaborations, one person who I consider in many ways is sort of the father of convolutional neural networks, he published the first papers on them back in the 1980s, is Jan LeCun at NYU. And we have a collaboration with him which includes our work on BB-8, the self-driving car, but also work on reinforcement learning so we can train these networks without labeling data for a number of different tasks, for reasoning and attention networks and networks with memory to sort of enhance the capability of these networks with more time sequencing and being able to focus the attention of the neural network on one aspect of the problem, on natural language processing and on medicine. So NVIDIA top to bottom is the deep learning AI company. It starts with the hardware where in the cloud we have our Pascal GP100, which you can get either as a DGX1 or shipping in products from IBM in a collaboration with SAP. In embedded devices, whether it's cars or drones or other embedded devices, with our Jetson and our Drive PX2 supercomputers, fueled by our Driveworks software package, and is enabling autonomous vehicles around the world. And then in the very near future, we'll be delivering our Xavier technology to give you 20 teraops in a 10-watt power envelope to power future AI systems. So we see this as just making the world a better place. Transportation will be revolutionized by AI. I think it's actually, at this point, more of a regulatory hurdle than it is a technical hurdle before we stop killing people by having humans drive cars. And that will just make our whole transportation system much more efficient. In addition to not killing people, self-driving cars can use the roadway much more efficiently. When humans drive cars, we've got to leave 5 car spaces between them in one direction and 1 in the other. So we're using less than 10% of the roadway. When the computers drive cars, we can use much more of the roadway and not have to expand out our infrastructure to handle larger volumes of traffic. We're going to revolutionize healthcare and our understanding of biology by doing deep learning. And ultimately, it will impact almost every aspect of society. So with that, I'd like to wrap up, and I'd be happy to take any questions that you have.
We have a shy audience.
Okay.
All right, well, let's thank Dr. Daly again, and he'll be around later as well for our panel. All right, I would like to introduce our next speaker. France Cordova is an astrophysicist and the 14th director of the National Science Foundation, the only government agency charged with advancing all fields of scientific discovery, technological innovation, and science, technology, engineering, and mathematics, or STEM education. NSF is a $7.5 billion independent federal agency with a mission that is vital to supporting our nation's economy, security, and the ability to remain a global leader. Cordova is President Emerita of Purdue University, Chancellor Emerita of the University of California, Riverside, former Vice Chancellor for Research at the University of California, Santa Barbara, Department Head at Penn State, and Deputy Group Leader at Los Alamos National Labs. She has served as NASA's Chief Scientist and is a recipient of NASA's highest honor, the Distinguished Service Medal. Her scientific contributions are in the areas of observational and experimental astrophysics, multispectral research on X-ray and gamma-ray sources, and spaceborne instrumentation. We are very proud to have such a person to be with us today, and I'd like you to help me welcome Dr. France Cordova.
Thank you, Greg. Thank you very much. Good morning. And thank you, Greg, for that warm introduction. And thank you, NVIDIA, for hosting this important conference. It's a pleasure to be with you. Advances in information technology over the last half-century have transformed our lives in ways too numerous to recount, although Bill Daly did a very good job just a minute ago. Yet the IT changes that we see unfolding today will have an even greater impact in our future. And one way that's highly anticipated, as you've been hearing, through artificial intelligence. But before I go into any depth about AI, I want to tell you just a bit about the National Science Foundation and its role in all of this. NSF was created in 1950, and as Greg said, is the only US government agency dedicated to supporting basic research and education in all fields of science and engineering. We work every day to support basic or fundamental research that engages the scientific curiosity of hundreds of thousands of scientists and engineers, educators, and students across the country. So let's go to the video to hear a little more.
The National Science Foundation, investing in research and researchers to create knowledge that will transform our future.
Well, NSF funding is absolutely critical to our staying in the forefront of high technology.
Without the support of NSF to that fundamental research, none of these would have been possible.
NSF funded my basic research, so we're on our way.
Without NSF support, I don't think I could actually do my research at all.
I always will owe a lot of my success to NSF.
NSF's really been what enabled us to go after and develop a high-risk technology like this.
Qualcomm was very small when it received its first SBIR grant with the National Science Foundation. We now employ something over 21,000 people.
The National Science Foundation provided all of the support for the research and the educational goals of the project.
NSF is in living rooms changing lives through funding.
What really causes economic growth is it's always innovation. So how do we get more of it? We invest in basic research. That's as simple as that.
As you just saw, NSF-supported research has tremendous real-world impact. We enrich the lives of many millions of people around the world, including each of your lives. In fact, NSF-funded research created the foundation of knowledge for many of today's innovations in artificial intelligence. We operate with an annual budget that's currently about $7.5 billion, and the vast majority of that, 93%, goes to support research, STEM education, and development of the STEM workforce. The Foundation's annual budget represents just 4% of the total federal budget for research and development, but it accounts for a quarter of the total federal support for basic research at our nation's universities and colleges. In many fields, in fact, NSF is the primary supporter. For example, in computer science, NSF accounts for 82% of the investment in academic basic research. We fund curiosity-driven ideas that push the frontiers of knowledge and discovery. These gains in knowledge have led to innovation with tremendous impact. For example, solar panels, 3D printing, the internet, life-saving technologies and therapies, and a lot more. As Eric Schmidt, former CEO of Google and current executive chairman of Alphabet, has said, NSF is where all interesting research gets started. This has been largely true for the field of AI. Consider self-driving cars, which we just got to see up close, technology that's becoming more ubiquitous today and made possible with years of early NSF funding. Advances in areas such as precision sensors, computer vision, planning and reasoning, real-time data analytics and predictive modeling, and control and automation have been integral in enabling the rise of autonomous vehicle technology, and NSF has funded advances in all of these areas. You have only to address your smartphone to get a sense of where AI is and where it's headed. And yes, NSF-funded research has helped to enable various components of that technology too. Advances in language processing and speech recognition technology have helped put AI at your fingertips. You can verbally ask for directions, and your phone can respond with the nearest gas station or restaurant. So I decided, as I was preparing this talk, to ask Siri if she's intelligent. Just thought I'd ask. So she responded in an even voice, "You will have to judge for yourself." I asked her if she could compose a song. I thought I'd just press it, and she gave me a playlist. I said, "Siri, can you dance?" And without a moment's hesitation, she said, "I'd rather sit this one out." But just give her time. AI is increasingly more common all around us and is evident in today's trend towards personalized everything. There are personal tutors to help you or your student in your home with math or learning a new language. Personalized in-home robots to help caregivers and even to clean our floors, and personalized medicine tailoring a treatment plan just for you. To ensure that we reap the benefits of personalized everything and of today's AI revolution and more generally, we need to be sure that we consider the social and policy implications. And we have a Directorate of Social and Behavioral Studies to do just that. AI is a frontier where both openness and security are required, but where innovation that is needed must be done in concert with changes in policy and law. If ever there were a definition of a compelling yet challenging field, AI is it. What excites me as director of the National Science Foundation is that the discovery space of AI is so immense. It has the potential to revolutionize everything we do. I'm in fact reminded of the late 1980s and early 1990s when I was a professor at Penn State. Here I am. Email was mostly used among scientists, and there were no websites as we know them today. At the time, we couldn't have anticipated that the digital realm would explode and that our world would never be the same. And AI has the same explosive potential. It has the potential to enrich our lives. It can help us enhance our performance and augment our human capabilities. But to get there, we need a lot more AI research. By expert admission, we, government, academia, industry, are underinvesting in AI. It's a point often made by Jason Furman, chairman of the Council of Economic Advisors, from whom you'll hear after me. He's observed, quote, "The biggest worry I have is that we do not have enough of AI." NSF agrees. And this is echoed in 3 recent reports. AI 100 is the first report of the 100-year study on AI and its influences. This report, published in September by Stanford University, makes the point that, quote, "throughout history, humans have both shaped and adapted to new technologies." Indeed, computing technologies and human societies are co-evolving, transforming each other in the process. The other 2 reports were released just 2 weeks ago by the White House in conjunction with the Frontiers Conference hosted by President Obama at Carnegie Mellon and Pittsburgh universities. One is a strategic plan, and the other is a vision document. These reports address the question, how can America best prepare for an AI future? They discuss the role of government and lay out a number of strategies and recommendations. Together, these reports cover the landscape of AI, from application sectors to potential impacts, positive and negative. The White House reports recognize the federal investments and that they're imperative to ensuring that AI is brought to bear on the challenges facing society today to help improve the lives of people across the nation and the world. NSF and fellow science agencies like NIH, NIST, DOE, and DoD, have a special role in supporting AI research. As you can see in this figure, our investments in AI generally support long-term, high-risk, fundamental research. Industry, on the other hand, often funds research over shorter time horizons that is lower risk and more applied with immediate high market relevance. NSF will fund long-term investments in AI research, enable effective methods for human-AI collaboration, and develop talent for AI R&D workforce. And we need that talent, so you can see there's a lot to do. We'll support researchers and developers, social scientists, and policymakers to seize the opportunities afforded by AI and to create the knowledge base to help overcome its associated challenges. And together, the efforts of government and academia and industry will help the US maintain world leadership in artificial intelligence. There are a number of hot areas ripe for increased research in AI. And I'm going to give you just a few examples. Large-scale machine learning. We've already seen computers reroute traffic because of busy intersections and diagnose illnesses of patients. Can a computer, with deep learning, perhaps address some of our questions about the universe? Being an astrophysicist, I'm wondering, about the nature of 95% of the mass energy content of the universe. Unknown. As an astrophysicist, I'd like to know that. Deep learning. Can a computer interpret a scene enough to recognize when a crime is being committed? Apprenticeship learning. Can AI teach robots to perform physical tasks? Natural language processing. Well, Bill Daly gave us some very optimistic news on that, but personally, I'm still struggling with my virtual airline agent when I call for reservations. Improved speech recognition in lots of forms could help here and many places. And of course, interdisciplinary studies of the societal impacts of AI, such as safety and privacy and fairness, are important fields. So the research landscape of AI is very broad, and NSF is invested in exploring all of it. Not only does NSF support research that advances nearly all areas of artificial intelligence, but we're also investing in foundational areas that are enabling AI technologies. We support basic research that helps to advance hardware and software. So just think about the ways in which advances in GPUs alone have helped to democratize computing, and in the process, open the door to a new AI revolution. And we're also investing in research areas that are driving the AI revolution, from big data to more powerful systems capable of performing data and computationally intense calculations. So building on these ideas and continuing to expand on frontiers of science and engineering, NSF recently identified 10 big ideas for future investment. They're bold ideas for the future, areas that NSF is uniquely suited to address. And I'm going to highlight just a few of those where AI closely aligns. The first I want to mention is shaping the human technology frontier. Our current focus in this big idea is on the workplace because it's a vast frontier. We want to start somewhere. So we're going to look at the future of work and productivity. Society today is on the cusp of a major transformation in work that's being driven by what you've just seen in the previous talk, by combinations of machine learning, artificial intelligence, the Internet of Things, robotics, and more. AI is gradually shifting towards intelligent systems that work with people, not in place of them. Indeed, for the last 5 years, NSF has led the National Robotics Initiative, investing in collaborative robots, what we call co-robots, that work with people on a variety of tasks and in a variety of settings. So think about your own businesses. Can you imagine how AI could just about do it all? While some current jobs may be eliminated, of course, several studies suggest that many new ones we can't even envision, will also be created. And without question, many jobs will require a tight interaction between people and computation, broadly construed. NSF aims to catalyze interdisciplinary research, as well as the education that's necessary to understand the benefits and risks of new technologies as we prepare for the future of work and productivity. A second big idea is a new emphasis on growing convergent research. We recognize that it takes all kinds of scientists, engineers, to address some of today's grand challenges. We need physicists and computational biologists, software engineers, programmers, statisticians, linguists, and cognitive scientists, among many others, all working together. And AI is inherently interdisciplinary. I know that many of you in this room are already using convergent approaches to develop exciting new technologies. So let me give you just one example. Recently, a convergence team of doctors, theoretical physicists, and computational biologists, supported by NSF and other foundations in the Stand Up to Cancer program, worked together to make a potentially groundbreaking discovery for pancreatic cancer. They found that mice with cancer, when treated with a combination of chemotherapy, immunotherapy, and a synthetic form of vitamin D, lived 50% longer than those given chemo alone. These results supported the theoreticians' conjectures that synthetic vitamin D could help deactivate a protein barrier around the cancer cells and enable more chemo to reach the cells. This was clearly a joint effort of all these people. And obviously what I've described is an oversimplification of highly technical research, but it illustrates what can be done through a convergent approach. A third big idea is leading the next quantum revolution. Building on decades of NSF-supported research, we're uniquely situated to address fundamental questions about quantum behavior and manipulation of quantum systems. This effort comes at a time when we're approaching the limits of Moore's law and in turn seeing new paradigms of computing emerge. Exploiting inherently quantum phenomena, such as superposition, entanglement, and squeezing, can help build more powerful computers, create exquisitely sensitive detectors, simulate physical systems, and enable new, secure ways of communicating. Quantum computing, for example, will require continued research on algorithms, programming languages, and compilers. These paradigms may help deliver new technologies for science, for commerce, and for defense. The next big idea identified by NSF that I want to mention is harnessing the data revolution. And we saw a beautiful case in Bill Daly's remarks for how and why that's important. AI feeds on data. So think about Watson, which outcompeted its human opponents 5 years ago in Jeopardy by quickly sifting through copious amounts of data. Could Watson, a super Watson, the next Watson, help figure out really intractable problems, such as the makeup of dark matter and dark energy, by quickly processing and synthesizing the large amounts of information already at hand, and simulations already available? Is the answer lurking now in the vast trove of data, in the publications, perhaps, of various languages? The last big idea that I want to leave you with is called NSF Includes. This idea aims to transform the way that we do education and career pathways to help broaden participation in science and engineering. NSF has long supported efforts to build a more diverse, inclusive workforce for all areas of science and engineering. In fact, we built the knowledge base and are one of the lead federal agencies for the White House Computer Science for All initiative. CS for All is designed to bring computer science education to all K-12 students across the nation, with access and equity at the core. NSF has been a leader in encouraging rigorous and engaging computer science education in our nation's schools. And just this past week, on Friday, I had the opportunity to attend and join the roundtable of the first kids science advisors at the White House. And yes, President Obama was present for this. These are his science advisors after all. And the young man, and I mean young, 9 years old, who started it all, this kids science advisors group, Jacob Leggett, when it came his turn to present his idea for changing up STEM education, he said, we need a computer in every single home. And here's some ideas about how to get there. Bringing computer science to all students at an early age will help to excite and empower them to pursue the field in AI in their careers. I'm fond of saying that of all of our 10 big ideas, includes is the most important, because once you've broadened the talent base, then who knows what new big ideas you're going to generate. The White House Strategic Plan on AI R&D notes that, quote, 62% of companies will use AI technologies by 2018, up from 30% today. That's a huge, quick rise. It goes on to say that AI experts are already in short supply, with demand expected to escalate. Universities and industries are in a battle to recruit and retain AI talent. So to summarize, we're well poised to embrace today's AI revolution. We need continued basic research to pursue the rich opportunities and challenges presented by AI. And doing so will help to ensure that the US remains a global leader. It will benefit the national economy, health, and defense, and it will enhance our lives, augmenting our ability to learn, to be more productive, and to address society's largest challenges. And by working together across academia, industry, and government, we can ensure that everyone can enjoy the benefits of AI. And that's a very big idea. Thank you. Thank you, Greg.
Thank you. Thank you so much. That was wonderful. I have the honor now of introducing our next speaker, Dr. Jason Furman. Jason Furman was confirmed by the Senate on October 1st, 2013, August 1st, sorry, as the 28th chairman of the Council of Economic Advisors. In this role, he serves as President Obama's chief economist and a member of the cabinet. Furman has served the president since the beginning of the administration, previously holding the position of principal deputy director of the National Economic Council and assistant to the president. Immediately prior to the administration, Furman was economic policy director for the president's campaign team in 2008 and a member of the presidential transition team. Dr. Furman has held a variety of posts in public policy and research before his work with President Obama. In public policy, Furman worked at both the Council of Economic Advisors and National Economic Council during the Clinton administration, and also at the World Bank. In research, Furman was a senior fellow at the Brookings Institution and the Center on Budget and Policy Priorities, and also has served in visiting positions at various universities, including NYU's Wagner Graduate School of Public Policy. Furman has conducted research in a wide range of areas such as fiscal policy, tax policy, health economics, social security, and domestic and international macroeconomics. In addition to numerous articles in scholarly journals and periodicals, Furman is the editor of 2 books on economic policy, and he holds a PhD in economics from Harvard. Please welcome Dr. Jason Furman.
Thanks so much. So the whole point of going through that bio was to establish that I know less about technology than just about anyone in this room. But what I try to do is think about how things will affect the economy, how they'll affect wages, incomes, jobs, growth, the thing that I deal with on a daily basis in my job. And in that context, have given a lot of thought to AI, what it's doing, what it could do, and what it means for policy, and want to share some of that with you. And it's very similar to what Francie Cordova was just sharing with all of you, and she actually stole my main point, so now there's no suspense left in that. I want to start out, though, by saying when it comes to AI and the economy, you often see people taking two different paths. One is, this is going to be a lot like what we saw before. The basic rules of economics work just fine for thinking about AI, and it's going to be continuity with what we've seen in the past. The other group says this is going to be something completely brand new. It's going to change all the rules of economics. The robots are going to take all of our jobs away from us. And then that group splits into two subgroups, the ones that are happy that the robots will be doing their job for them because they didn't much like their job before, and the ones that think we'll all be sort of miserable, unemployed, and one person will own all the robots and get all the money. I'm pretty firmly in that first camp, which is I see it much more as a continuity with what we've seen in the economy. But I think even that continuity is going to raise a set of challenges because technology's created challenges over the last couple decades, and AI will continue those challenges. And so I want to talk about what those challenges are today. But I especially want to talk about the biggest challenge, which is so far the biggest worry we have, and you heard this, is that we don't have enough AI yet, and we need more of it. And our first, second, third reaction to new innovations, new technologies, should be to be really excited about it and think it's going to help our economy. Then maybe our fourth and fifth are to worry about some of the side effects and what we can do about them. But let me start with this question of, is this going to be something different? And certainly, if you look at an awful lot of headlines over the last couple months, you'd think the robots are coming to take all of our jobs. And I should, by the way, disclose that my slides are more in line with an economics seminar, which is to say considerably duller than the slides you just saw. So I want to, in addition to my technological knowledge, you'll see that manifested. So if you look just at the last couple months, every day there's some headline about the robots taking our jobs, AI taking our jobs, the machines taking our jobs. It turns out, you see the same headlines going back to 1935 with robot brains outdo man's mind in speed and accuracy of results. You see it in the 1960s about they bid for the big jobs, both in outer space and even here in the United States. Automation in Britain, stirring unrest and labor. Mr. Robot outshining his master. So this is something we've been worried about for a while around robots. And then if you go past robots, for even longer than that, people have thought for thousands of years that machines would replace people. And what you find is the basic economic law that machines make you richer. Richer people want to spend more money, and that grows the economy, first of all. And that second of all, machines do replace a lot of the jobs. Most of the jobs we had 200 years ago, we don't have today, but they create new jobs, helping to provide the goods and services that people want with all of the additional money that they have. And that's why we've constantly thought this, we've constantly worried about this, we've constantly been wrong. I see no reason to think that this time is going to be any different. But let me start with my first worry, though, the worry that we don't have enough AI. And I have a little bit of whiplash because I travel in a lot of different circles and different groups. And when you're around technologists, they're all telling you about their latest invention, how exciting it is, how it's changing everything. But then I go to a group of economists, and they're all sort of a little bit Eeyore-ish depressed about the latest productivity growth statistics. And if you look at those productivity growth statistics, they really have been quite disappointing in the last many years. And this is true across all of the economies, all of the advanced economies. In fact, the IMF lists 31 economies that they define as advanced. In 30 out of the 31, productivity growth over the last decade was lower than what it was over the previous decade. If you look at the United States, for example, from 1994 to 2004, productivity grew at a 2.3% annual rate. From 2004 to 2014, it grew at a 1.1% annual rate. Now, the argument you always hear is that the people who do these statistics are missing a lot of stuff. They're not measuring all of the great innovations we have around us. And I think that's absolutely right. I think that 1.1 number for the last decade is too low, and the productivity growth was 1.1 plus X. I'm not sure exactly what X is, but it's some decent number. The thing is that was true before, too. That 2.3 is also too low, and productivity growth in that decade was 2.3 plus Y, and X and Y probably aren't that different. If you think 1994 to 2004, that's the decade we got the internet. Google started making our reservations online, e-commerce, got cell phones, got mobile email. There was an enormous amount of innovation in that decade, much of it that we were missing from the economic data. Just like in the last decade, there's been a lot we've missed. It's not obvious to me that it's more or less in either one, and economists who've studied it have come to the same conclusion. Part of why our intuition about the magnitude of productivity growth and the actual magnitude of productivity growth as measured by the statisticians are so different is that our imaginations overweight the cell phone that we're holding in our hand and staring at for too much of the day, and underweight the fact that most of our economy is things like housing, restaurants, healthcare, education, etc., some of which are making progress technologically, some of which aren't, but none of which are going through the type of really rapid transformation that an important but still quantitatively relatively small part of our economy is going through. That being said, that part of our economy is going through an important transformation. AI is part of it. AI embodied in industrial robots is one way to measure that. And studies that look at industrial robots find that from 1993 to 2007, they were responsible for 0.4 percentage point per year on our productivity growth, which is a large fraction of the overall productivity growth we have. AI, as everyone in this room knows, is making progress in areas that range from healthcare and radiology to detecting customer fraud to being deployed in the criminal justice system. And I think there's a lot of reason to expect that that's just going to accelerate and grow in the years and decades to come, which is why people, if you've heard of economists like Robert Gordon, I wouldn't subscribe to that type of I'm certain the future is going to have slow productivity growth. We've often seen waves where it takes time to figure something out and deploy it in the economy. But it's still the case that when we're thinking about our own jobs, first of all, to date, AI really needs to be trained very heavily in one area and then needs to be retrained very heavily to go to a new area. It just can't wander from place to place on its own. You teach it how to recognize a cat, that takes a while, and then you need to do a whole new process and a whole new set of programming to teach it to recognize a table. And when it comes to that, it tends to be, at least to date, not quite as good as a 3-year-old. The other thing about AI is there's a whole set of things that it's quite good at, things that involve, for example, pattern recognition that lend themselves to machine learning. But there's other things like social cues and creativity that humans are not just better at to date, but I think are likely to be better at indefinitely. And that's why the robots taking our jobs, the observation of a couple millennia of experience with technological improvement, the basic economic theory that as we become richer, we want to buy more, and that creates new opportunities for jobs, are part of why I think that. But part of why robots don't take all our jobs is that we're willing to underbid them when it comes to work. And that's a particular fear around AI. Two professors at Oxford, Frey and Osborne, did a study that got widely quoted saying that 50% of jobs are at risk of automation. Now, that's over a couple decades. You could quibble with the numbers. As I said, that doesn't mean those jobs disappear and we have a 50% unemployment rate. But what we did was we took a look at the Frey and Osborne numbers and coded them by how much each occupation is paid. And we saw something really dramatic. If you make less than $20 an hour, in their numbers, your probability of automation is 83%. Between $20 and $40 an hour, it's 31%. And if you make more than $40 an hour, it's 4%. Now, you could argue with those. Maybe the 83 should be 93. Maybe it should be 63. Maybe the 4 should be 24. But the results and the differences are quite stark. And that gives rise to the first fear, which is in the last couple decades, technological improvements have complemented the skills of highly skilled people, have enabled them to earn more, and have replaced some less skilled people and contributed to rising inequality. And this is the share of income going to the top 1% in the G7 economies. And you see it's risen everywhere. It's risen further and faster in the United States. The other thing you see here, though, and this is a really, I think, important lesson, is the share of income going to the top 1% also varies a lot across countries. It's not like technology said, this is how much the top 1% is going to get. This reflects institutional choices, policy choices. It's within our concern. The second point is that while to a first approximation, the idea that robots will take all our jobs, I think, is wrong. That, for hundreds of years, in any given year, about 95% of the people who want to work can find work. But we've had a problem in our economy that for decades now, the labor force participation rate for prime-age men, that's between 25 and 54, has fallen. And for about the last 15 years, we've seen the same thing with women. And part of this isn't that your job is replaced, there isn't a new job, but let's say 10 people lose their jobs, 9 of them have no problem getting new employment, but 1 of them maybe doesn't, and they don't get back on their feet very quickly. This problem isn't a technological problem. Again, it's a function of our institutions and our policies. And one way to see that is to look at the labor force participation rate across the OECD. The first thing you'll see, this is for men between 25 and 54, the first thing you'll see is that we're tied with Italy and just ahead of Israel. We're about 10 percentage points below the labor force participation rate in a country like Switzerland. And just to put that in context, when our unemployment rate goes up by 2 percentage points, we pretty much think we're in a recession. If it goes from 5 to 7, we say that's a recession. It's an extra 10 percentage points difference. Another thing is these dots show us where we were in 1990, and what you can see is the United States had the second largest decline in male labor force participation from 1990 to 2014 of any of these countries. And then the last thing you see is, if you look at Italy versus Switzerland, for example, one of them has 88% in the workforce, one has over nearly 95% in the workforce. That's not because Italy had more robots that took more jobs, or Italy had more automation, or Italy had more technology than Switzerland. That's because they had different labor market institutions, different ways of matching people to jobs, different things that are very much within the control of policymakers rather than something that just happens to us. So what are the implications of this? The first thing is we need more artificial intelligence. We just heard a really important set of arguments for the role that public research plays in that, and let me underscore those arguments. We invest, and maybe I'm getting the number wrong, I think about $200 million a year in AI at the federal level. Private investment is $2.4 billion, so we're never going to be able to match the private investment. But our investment is really important. You see, in R&D, private investment in R&D is at a record as a share of the economy, and that's a great thing. But public investment in R&D has declined as a share of the economy pretty much since the 1960s. And we do 60% of the basic research, and there's not as much of an incentive for the private sector to do that basic research for all the reasons that we saw before in terms of it being less commercializable, the benefits spilling over to others. And some economic studies have found that the optimal level of publicly funded R&D is about 2 to 4 times what we're doing right now. We're not going to be able to quadruple our budget tomorrow, apologies, which also means we need to be smarter about how we spend money, and we've done a lot of that. So for example, DARPA did a challenge on driverless vehicles that played an important role in stimulating the research and innovation that is getting us to driverless cars a lot faster than anyone would have expected a decade ago. So you see there a role for public investment, for smart spending like competitions, and its embodiment on the private side. The second thing is workforce. Computers can beat humans at Go, chess, and Jeopardy, but those computers needed to be programmed by humans, and we need humans in the pipeline contributing to AI. And there's a lot we can do in terms of workforce development, as well as reforming our immigration system to make sure that we're bringing in high-skilled people, making sure they can stay here while dealing comprehensively with the set of people in the United States already. A third area is competition policy. This is something that the Council of Economic Advisors has been doing a lot of work on, and having a competitive marketplace is one of the best ways to spur innovation, and that's especially true in the technology sector. A fourth area is privacy. Having privacy is one of the things we need to make sure we have the confidence in using technology, using the internet, giving ourselves over to automation. And we've put forward a multi-stakeholder approach to move forward on that. And the last one that I would underscore is cybersecurity and the unique set of challenges that AI poses in the area of cybersecurity, but also the opportunities that it affords us to deal with some of the cyber threats. That's everything we need to do with AI. At the same time, we need to move forward and continue to deal with inequality, continue to deal with labor force participation. I don't think that is a brand new problem that requires a brand new solution like universal basic income. I think it's very much what we've been grappling with. So more education, higher minimum wage, expanded voice for labor, better ways to help people search and get into jobs that build on the efforts we've done would help deal with any of the negative side effects that we get from artificial intelligence. So in summary, I'd say I think it's a very exciting area for our economy. I think it could be very important going forward. We really do need more of it. We don't need brand new economic policies to make it work, but we also don't need to believe that technology determines answers in our economy. Those very much are affected by our policies, our choices, and it's important we have the right ones. Thank you.
That was great. Well, that concludes our keynote sessions, and we have 3 options for you now. We're going to take a few minutes to reset our set for a panel discussion coming up. First, if you're on the technical side, you can attend the technical sessions and the Deep Learning Institute training starting now in the assigned rooms you'll find in your guide. If you're primarily interested in what government and industry are doing to advance AI in the United States, you can stay for our next panel, which is starting here in a few minutes, about 5 minutes, so 11 o'clock to reset things. Otherwise, lunch is available starting now in the Atrium Ballroom, and it will continue until 1:30 along with the exhibits. So if you're looking to connect with NVIDIA staff, you can find anyone with an NVIDIA shirt on in the exhibits, the DLI training labs or session rooms. And I think this is going to be a great GTC. Would also like to invite you to our larger conference in Silicon Valley coming up in the springtime, where you will find 8,000 attendees and a much larger multi-day program. So thank you very much for your time and attention this morning, and I hope you have a great conference.
As a courtesy to those around you, please silence your mobile phones and all other electronic devices. Thank you.
Okay. Good morning. Thanks for joining us. Let me welcome you for probably the second or third time to the GPU Technology Conference. My name is Matt Shears. I'm Vice President at the Computer and Communications Industry Association. I will be moderating our next panel on preparing for the future of artificial intelligence. As you may have noticed up until now, previously, most of the stories we hear about investment and activities around artificial intelligence involve the business community's embrace of artificial intelligence. But today, we've already heard a lot about what the federal government is focusing on in the context of AI, and we're going to continue that discussion. Earlier this month, the administration issued the report Preparing for the Future of Artificial Intelligence, which considers the economic and policy implications of AI and offers a number of recommendations about what the US government can do to prepare for, encourage, and manage AI in the marketplace. So we are fortunate to have our acclaimed group of experts here to continue that discussion with you today. And I will introduce our guests. More extensive bio information is available in your conference materials. To my immediately left, we have Bill Dally, NVIDIA's Chief Scientist and Senior Vice President for Research, whose pioneering work in parallel processing at NVIDIA and prior to that Stanford helped shape the AI revolution. To his left, we have Lynn Parker, a Division Director for Information and Intelligence Systems at the National Science Foundation. Lynn directs NSF research on AI, machine learning, robotics, sensor networks, brain and cognitive science, human-robot cooperation, and embedded systems, overseeing a $200 million annual research budget. To Lynn's left, we have Victor Bennett, a senior economist at the White House Council of Economic Advisors, where he provides policy input on innovation, technology, and industrial organization. Victor is on leave from Duke University, go Blue Devils, where he's a professor at the Fuqua School of Business. And to Victor's left, we have Alan Davidson, the United States' first Director of Digital Economy at the Department of Commerce. Alan's previous roles included Director of New America's Open Technology Institute, a research affiliate at MIT's Computer Science and Artificial Intelligence Laboratory, and Director of Public Policy at Google. So you can see we have a wealth of experience here, and to take advantage of that, we are just going to jump right in. Our speakers will give a few minutes of remarks on the subject, then we'll have some discussion, we'll have Q&A, and if we have time at the end, we will take questions from the audience. So our proposal to manage that most efficiently is that you can simply email me. Here's my email address up here on the screen, so shoot me an email, and I'll try and work your question into our conversation. If you need the Wi-Fi, it's on the back of your badge. So why don't we begin? We'll start with Bill. Do you want to get us started?
Yeah, so I'm very excited about, I guess as you could tell from my keynote, about artificial intelligence and what it can do for the country. And I think now is one of these moments where we kind of have to seize the moment and really double down and apply a lot of resources, because we are in a globally competitive environment, and I think artificial intelligence is going to transform our future. To self-driving cars, which will make far more efficient use of our transportation infrastructure, reduce deaths on the highway. We can have individual artificially intelligent tutors for every child that adapts learning to their needs and their interests and makes it exciting for them. I think medicine is going to be transformed. But I think that it's a global race now to see who is going to be the leader in artificial intelligence. I think the fact that the US is a leader in a lot of the cloud and mobile computing has to do with investments that were made back in the 70s and 80s, when DARPA did the ARPANET, which ultimately evolved into the internet, and when actually a lot of the foundations for artificial intelligence today were developed. And so I think that there's some big needs to lay the groundwork for our competitive position in this future by investing in future research that will lead to even better AI, and also investing in a workforce by making sure that our colleges and universities are educating the type of people we need. As people say there's a huge shortage of programmers today, but actually as AI changes the rules and computers basically program themselves by learning, what we need to be a programmer changes. It's no longer somebody who writes code. It's somebody who's more of a data scientist, who curates the data, who understands neural networks, can configure them to solve a certain task. Now I do run into people who say they're worried about not just their jobs getting taken away, but by robots taking over the world and enslaving us. And quite frankly, I can't imagine that happening, because I don't think we'd be very useful to the robots, among other things. If they're smarter than us, they can find better beasts to lug their stuff around. But I think that there's also an issue with educating the public to make sure they understand what AI can and can't do. We train a neural network for certain tasks. It does just that task. It's not going to go beyond that and develop other capabilities and become a threat to us. I think there are also issues of data sets where in many ways a real gating item to progress is the availability of large curated labeled data sets for whether it's things like images and speech, but in other applications as well, medical applications, having lots of images of skin cancer that are labeled, this is skin cancer, this is just a mole. And you talk to people, so yeah, I've got 500 images, but to train these networks to be powerful, you typically need millions of images. With techniques like transfer learning, you may be able to get by with hundreds of thousands. But I think that one of the real gating items to being able to apply this to many areas is to have data sets. And today, many of these data sets are closely held by private companies. And a big role for the government in this is to, in areas where it makes sense, to have data sets that they make widely available, both to spur research and for public benefit.
Lynn, do you want to continue?
Sure. So, no, AI is not a new concept. I think we all know the history of AI. It's been around for 50 or 60 years. And to me, as someone that has been in this field for many years, it's exciting to see the public excitement about AI. And you wonder, well, why is it now? And certainly we've heard a lot about the importance of the hardware. But if you look at the investments and the convergence of technologies that are available today, we see obviously computing hardware of all shapes and sizes, from the high performance computing down to the embedded computers, is an important piece. You have sensors. You have sensors everywhere that are helping us measure things from the state of the oceans to the state of our road and highways to the state of our grandparents' homes so that they can stay longer in place and age in place. So this sensor data is helping us digitize the world. It's creating lots and lots of data. And so we have algorithms that can make sense of this data. They can turn data into knowledge. And then we can turn knowledge into action through things like robots. Lots of advances in robots, lots of advances in intelligent control systems that can affect the world in ways that we find useful. And then, of course, these computing devices, the sensing, the actuation devices are all inter-networked now. We have great networking technologies that allow these systems to talk to each other. You have cloud resources that are available to the robots and to the sensing and to the computing systems. So that now it even makes sense to talk about a robot in Europe teaching a robot in the US through shared knowledge that goes up into the cloud. And so, and then on top of all of this are intuitive and natural human interfaces to all of these technologies. We have brain-computer interfaces, brain-robot interfaces. We have tactile interfaces. We have every kind of sense that we have. There's some sort of way to use that sense to interface with all of these technologies. And so we have this vast landscape of sort of converging capabilities and technology that are leading to this excitement that we hear today in the popular press. But it's a lot of research. Obviously, NSF, we heard from Dr. Cordova earlier, and other federal agencies have invested significantly in these areas. But it's important to step back and say, okay, we've made these great investments. Now we see the growth of industry in all of these areas, and we wonder, what is the role of the federal government in R&D? And so that's why back in the spring, at the direction of the White House Office of Science and Technology Policy, we began the development of a national AI R&D strategic plan. And so I co-led the task force that generated that plan. And just to give you the cliff notes of that plan, it's available online, but the gist of the R&D strategic plan for AI is really to focus, as mentioned before, on the importance of long-term investments in AI. So there are many directions. You can see, well, what are the theoretical limitations of AI? We don't really know. We'd like to figure that out. How can AI systems behave in a way that humans can understand, sort of like human-like AI? So for example, many deep learning systems make mistakes that humans would never mistake. You see a screen of noise and you say with high confidence it's a leopard. Well, you don't understand that, and so that reduces your trust and confidence in the system. So there are many areas of fundamental research as it relates to AI that we need to have answers to, and certainly the federal government has a role here. Humans work with AI, and so we need to be able to have humans collaborate and cooperate and be enhanced by AI technology. So how do we have those interactions operate in a productive way? How can we ensure that AI systems are obeying some sort of ethical norms of what we expect AI systems to do? We may say, just like Asimov's rules, it'd be nice if those really worked. They don't really work, but we do have expectations for how the AI systems ought to behave. Well, how do we engineer AI systems so that they are guaranteed to obey those ethical norms or the norms that we expect for how the AI should behave? How can we guarantee that they're safe? How can we verify that they will behave as we want them to behave? How can we ensure their security? These are important questions. Data sets is an important part that comes out of the need to be able to test and evaluate these systems. We need to have metrics for evaluations and standards so that we can compare the various systems. And of course, workforce is really important, and we need to be able to do what we can in order to foster a healthy AI R&D workforce. So all of these are topics that will show up that do show up in the National AI R&D Strategic Plan that we believe are important areas for federal investments to advance AI.
Thanks. Victor?
So I want to take a step back and flip the artificial intelligence in America's future and talk about America's future first. So the CEA was founded 70 years ago with the goal of providing economic advice to the president to prevent a second depression. And we're still around, and our goal is still to take economic theory and provide help with the challenges of the day. And one of the big challenges of the day, which Jason mentioned, is that global productivity is really low, that we have always expected each generation to have a better life than their parents. But from 2004 to 2014, we had 1.1% growth, which was less than a half of what we had the generation before. So given that, it's probably not surprising that AI has caught our attention, because we think and we hope that this could be one tool that gets us back on track for growth and improving the lives of everyday Americans. And so the question is, if all of this is being done by the scientists, why is there even an economist up on his panel? And essentially what we think our role in this whole thing is setting the rules of the road. We want to make sure that the tools are there for the scientists to be able to be productive and impactful, and we want to make sure that the rules are there to make sure that that impact is broadly felt across Americans.
Thanks.
Short and to the point, I like that. Well, first of all, thank you for having us here today. Thank you for the organizers for putting this together. I think we're all here because of a common belief that AI represents a tremendous opportunity for the American economy. part of the reason for this panel is because it also raises some interesting policy issues and policy challenges that we need to address. Artificial intelligence is here, it's been here. I think we at the Commerce Department share this belief that it's essential for American competitiveness. It's a tool of improving productivity, and it also is improving people's lives and will continue to have incredible potential to improve our lives. But the other thing that we, I think, all need to recognize is that we will only maximize that potential, really only realize that potential to improve people's lives if we address the really serious policy issues, the social implications that are being raised now, and those we need to take those seriously and think about them. The starting point for us is, as a lot of people have said, that there's incredible promise in AI today. It's opening up new markets, creating new products for people, smart vehicles, improving road safety, smart buildings, saving energy, precision medicine, saving lives. And we've heard about this very eloquently earlier today, and it's truly an exciting time. I will just say personally, my own experiences with AI have been very real over the last week because I got my Amazon Echo, the little dot, and we've been playing with it a lot. And it is hard as a fallen computer scientist, it's hard not to marvel at, just to recognize our voices in the middle of chaos, to understand what we're saying, to put some context to it and give a search result back, to speak that. I mean, I find it a miracle every day, and I will tell you that the killer app in the Davidson household seems to be using all that incredible power to ask for what the weather is outside. We just do it over and over again. It is kind of a little miracle. I'm sure there are bigger and better things to do out there, but these little miracles in everyday life, what's the saying from Arthur Clarke, that sufficiently advanced science is indistinguishable from magic, right? So we're experiencing that magic, a lot of us, in our everyday lives today. At the same time, there are these incredibly interesting and important challenges that we see on the horizon, and I think the White House report also does a really nice job, the administration's report on this, spelling out some of those challenges that we need to be addressing, starting with issues like, I'll just tick off a few of them, hopefully we can talk more in the Q&A, but safety of systems is going to be huge, especially now that we see this kinetic connection in a lot of ways to the systems that we're building and how they're involved in our lives. The related questions of security of systems and the difficulty in some ways of understanding security in these very complex systems that we're building. Privacy is an issue that comes up with access to data and access to a lot of what happens in our lives. The workforce issues that CEA has really done a nice job at spelling out and helping us understand. Inclusion issues, the question of algorithmic bias. Some of the issues that have come up were highlighted in the prior administration reports on big data, for example, are things that we're going to need to be thinking about. And fairness, how AI will be applied and how we're building systems that use it. Some of these issues are going to be handled by existing regulatory agencies. We see this, for example, with Department of Transportation and NHTSA and their approach now on autonomous vehicles and connected vehicles. Some of them are issues that we've been facing for a long time in the internet space. Privacy is not a new issue in this space, but there does seem to be something special and new about these systems, the scale of the systems, the complexity of the systems, and the importance of these systems in our lives that's going to really demand our attention in this space. And so government has a real role here. Part of it is the R&D role that we were just talking about and that Lynn was talking about. We at Commerce are doing our piece of this. We've got some interesting, about I think $11 million in grants and R&D activity happening this year out of NIST, the National Institute of Standards and Technology, doing work on AI and cybersecurity, thinking about doing some image recognition standards, and it's exciting and fun work. And so those are examples of how government can be involved in the R&D side. But we also need to be thinking about how we can help take on these big policy challenges and engage with them early. This is going to be an area where we need to be in partnership with the private sector. The government is not going to figure out all the answers on its own. In fact, in some ways, the best things that happen are when we address these issues early in the product development life cycle, and we think about issues of security, issues of privacy, baking those in, building them by design before they become big regulatory issues. And And we want to be a partner in doing that. We're also working on opening up data. Government can also is a big user of AI systems and will be a big user. So deploying systems that have good governance mechanisms, good policy approaches ourselves is going to be an important role for government. And I guess I would just say in closing, we at the Commerce Department, we spend a lot of time talking to business leaders, CEOs, leading technologists in the space. Everybody we talk to feels quite confident that we will be able to build these really important and interesting systems from a technical and business point of view. The number one thing we hear now is concern about the social implications, the policy backlash. How will foreign governments approach some of these issues? And so we, as government, need to be engaged in this. We want to be a partner. And I will say, this is a place where we need your help. This is not a place where government alone can do it. We need the help of people in this room who understand the technology, who want to engage in the public policy conversation, to be thinking long-term about how we address these big issues. So thanks for starting the conversation.
Thanks, Alan. Yeah, with that being said, let me first ask folks if anyone wants to take a minute to respond to anything the other panelists have said or build on what you've already heard.
Hear, hear.
Hear, hear.
Amen.
All right. Well, all right, a specific question. We've talked a lot about specific policy issues that might arise, but maybe we could drill down a little bit into what role the government might take in responding to policy issues. I don't know, Lynn or Alan, if you want to talk about from the policy perspective, what role the federal government might have in addressing some of the questions that we see arising in relation to AI.
Well, I think it's important to recognize, of course, I come from NSF, and we're interested in the R&D, but I think it's really important to recognize that the R&D informs policy, and policy informs R&D. And it's a very important interplay. As an example, perhaps you want to ensure the safety of, say, a driverless car. Well, the regulators, the policymakers may need to say, okay, here is a characteristic of that vehicle and the way that it operates that we need to be able to ensure it behaves in the way anticipated. And so that then presents a research question. We know exactly what they need in order to be able to provide the policies that say this is okay to drive on the road. And so now the R&D people can go back and say, okay, we have to address this difficult R&D question about some properties of how the system operates. So I think it's really important to recognize that it's not just about regulation and policy independent of R&D, but the two have a very close relationship.
So I would second that to start with, and I think especially there is real research needed in a lot of these areas to help us understand how we address issues of security, issues of privacy. I think we can help in a number of ways. There are going to be areas where, as I said, where safety, for example, where regulation exists already today, and we have to think about how to play in that space. And I think one of the things we also need to be really conscious of in government is how to make sure that we're doing that in a way that's consistent with innovation, that supports innovation and competitiveness, and recognizes the importance of these technologies. In some ways, we will be, we can help by being an issue spotter and use our bully pulpit to convene around these questions. And we've certainly done that in areas like privacy and cybersecurity. Something like the NIST cybersecurity framework is a great example of where we've worked with industry to develop a framework. It's not a top-down regulatory approach. It's something that's flexible and is developed with industry to think about how to address these kinds of problems. And I think, like I said, I think the issue spotting role right now, we're in early days here, is really important because, as I said, I certainly saw this from the private sector side. If we can be, people talk about baked-in cybersecurity, privacy by design. Those are real things that we need to be working on because if we can address these issues head-on before they become big problems in the regulatory environment, it's much cheaper, it's much more efficient, we support innovation, and we head off big challenges. So I think we are trying to build our muscles within federal government to be engaged in these conversations, to be a good representative of U.S. industry abroad, because these issues are going to come up. They're coming up in Brussels, they come up in Beijing, and we want to help develop international frameworks that make sense too.
So I'd like to build on that. Lynn raised what I think is probably the first way that people think about government's involvement with science, which is financing. And I think that's extremely important. Alan and I both in previous lives worked at Google, which came out of a DARPA-funded project on digital libraries. The NSF funded my dissertation. So I think these are incredibly personally important roles. And then Alan talked a lot about security. I think there's another role that has been talked about less, but that I'd like to bring up, which is competition policy. Recently, the president issued an executive order talking about the importance of competition, both to keep down prices and to increase innovation. And one area in which AI is somewhat special is the importance of data. And so if we can make sure that the data needed to train these algorithms and to make them better are broadly accessible, then we can make sure there's a lot more competition in the AI space and that no one company comes to dominate. And that'll be better because it'll lead to more competition, and it'll lead to more innovation, and it'll lead to lower prices so that Americans broadly can take advantage of these technologies.
Yeah, so as the sort of private sector representative here, I pretty much agree with what's been said, but I sort of view the real role of the government here is to come up with regulations that speed our deployment of AI technologies rather than slam the brakes on until everything is completely understood. And I think it's really a question of striking the right balance between complete safety and progress. And self-driving cars are a great example. They're not perfect today. They probably never will be perfect. But I think already today they're to the point where if they were deployed, they would save lives and make better use of infrastructure. So I think it's in the government's interest. It's done state by state today, but the federal government should put out guidelines that the states hopefully will follow for here are the safety regulations we should have. And certainly they put out the rules for safety of newly manufactured vehicles. And those regulations need to be put down in such a way that they don't strive for perfection, but they strive for improvement. And you could even go so far as to say it's a public good to save lives on the roads. And much like no drug manufacturer would make vaccines if they weren't indemnified because of the legal hurdles. You could imagine similar indemnification for self-driving vehicles, where because it's a public good, because you're saving lots of lives, you basically will indemnify the people who make the self-driving vehicles from the few people who actually will get killed, because far more people are saved. So as a person in sort of the business of AI, I'm looking to the government to set up an environment which allows us to move forward, because our competitors around the world will. And if we become overly cautious and hold AI back, it'll be a lost opportunity.
And to Bill's point, the White House recently issued, along with the DOT, some guidelines for autonomous vehicles. And if you are interested in autonomous vehicles and haven't had a chance to read them, I highly encourage you to do so.
So one of the questions that I've seen come in, I've been watching all these great questions come in by email. One of the questions that's come in a variety of forms and is close to something that I'd noticed. The recent White House report, one of the recommendations pretty much just says, monitor AI in other countries. And we've had a number of references to competitiveness. I guess maybe I could ask folks to comment on sort of the relationship between AI and competitiveness, what other countries might be doing that we should be looking for, and is there anyone, one of the questions here is what country or countries might actually be relevant to our AI policy? So I don't know if anybody wants to take a stab.
I can take a little bit of a stab at that. I view it not so much as competitiveness, but also as collaboration. But ultimately, some companies are going to dominate in this area, and I think a lot of the economic benefits of AI will wind up in the countries where the companies that dominate are based. I actually have research projects in collaboration with people at Tsinghua University in China. And I see China as investing hugely in this area, and actually in a lot of computer science in general, with huge government support for building supercomputers, for doing AI research, and for the like. And we work with them, but we also see that NVIDIA as a company, we would like to make sure we are the dominant player in hardware for AI, and if foreign governments are investing heavily in their hardware manufacturers, we hope that our government will be investing heavily in R&D in the U.S. so that we can basically maintain our lead and not be surpassed because of huge government subsidy.
If you look in the National AI R&D Strategic Plan, we have a chart in there that shows it picks out deep learning in particular, and it's by nation over the last several years to look at the number of publications in deep learning, and including the number of publications with at least one citation. And China has surpassed the US in terms of first authors in the area of deep learning. We didn't do a broad survey across all of AI, but I think that's a representation of how much involvement and the other nations are growing somewhat, but not as much as the U.S. and China. So I think that's a representation of the impact that these technologies can have. It's recognized not just here, but as Bill mentioned, in China as well. So I think that's an indicator that there's a lot going on in this space.
Particularly on the policy side, I would put Europe on the list of regions to watch. Certainly, I was just a couple weeks ago in Berlin, and one can't help but look with some admiration actually at the very strategic approach they're taking to some of these big technology issues, including artificial intelligence, particularly within their Industry 4.0 rubric. So there are countries out there that are being very strategic about this, investing quite a bit, particularly some ways, not necessarily even in the most consumer-facing side, but maybe more on the industrial side, looking for productivity gains there in manufacturing. So those are all things to watch. On the regulatory and policy side, we are very aware of wanting to make sure that they're, as we think about the global regulatory picture, that we are seeing regulation or policy that supports innovation, as Bill said, and doesn't hinder it. And we're very aware, I think, at least from our department point of view, looking to make sure that there aren't barriers to market access arising through some of the rules that are coming out there, that they are supporting innovation, that they treat foreign competitors fairly. We want to make sure that we're supporting U.S. industry even as we look for global frameworks that are going to work in this space and help make sure that we're dealing with the big policy challenges.
I think one of the values of monitoring everyone else who's working in a space that you're working in all the time is to figure out what works that we can try to take on. I think one thing that the United States has been relatively successful recently with is improving access to STEM education. We're finally up to a level where 12% of degrees are STEM, that's 20% for females. And if there are things that we can learn from different countries' educational systems that can help us be ready for some of these new jobs, I think that that's tremendously valuable.
If I can add one other point too about monitoring, I know certainly the U.S. government is interested in the security of the American people, and I think if you obviously read the press, and there's a lot of concern about AI taking over the world, the singularity effect, that suddenly it's going to be so smart that we don't know what will happen. So I think in some sense there's also a piece of due diligence there to say, even though most reasoned people don't really think that we're going to get to some situation where AI is about to take over the world, in the sense of due diligence, you might say, okay, let's monitor for research advances internationally and see, has someone somehow hit some important milestone that now we are going from narrow AI, which can solve very specific kinds of problems, to a more general AI that now is more human-like in some sense. I think most people believe we're very far from accomplishing that, but if it happens, we want to know it's happening. So I think there's also that sense of due diligence.
Yeah, another thing on sort of the international collaboration front is I think we still have, I think, what are regarded as the best universities in the world doing research on computer science and AI, Stanford, for example. And I think because of that, we attract the best and brightest people from all over the world to come here and study. And I think that when they get their PhDs in computer science, particularly in things related to deep learning, we should issue them a green card right at that point, because these are really valuable workers, people who bring great economic benefit to our country. But instead we say, go home, right? And now go through this tedious immigration process to come back. And I think that's completely counterproductive. We need to find some way of reforming our immigration laws so that we can take advantage of the fact that we're attracting these people here, as well as continuing to support the leading research universities so that they continue to come. I actually was not aware of your statistic that the Chinese are out publishing us in this area, at least on numbers, maybe if not on quality, and that worries me that the best and brightest may start going there to study instead, and then we'll be cut off from a critically important resource.
I feel that the education and immigration issues border on something that I've seen a couple folks touch on, and I saw at least one question come in, which is the workforce development issue. Obviously, those are some issues there are some steps that might be taken in relation to workforce development. Are there other things that policymakers should be thinking about in the context of workforce development and training, sort of preparing Americans for the AI economy?
As a computer scientist at NSF, I'm particularly excited about the CS for All initiative, which is really aiming at getting computer science into the K through 12 classrooms. I think our children need to be able to think computationally and have experience programming, and I think that will help in training people to, these new jobs of the future are going to, many of them are going to be heavy computer science oriented, and so it provides more people the opportunities and the background, the underpinnings of education that they need in order to enter these fields. I think it's hard to do if you don't have some introduction to that in K through 12.
I mean, this is absolutely going to be one of the biggest issues and challenges. I think the CEA report, of course, talks quite a bit about these changes in the workforce that are coming, and we just need to be aware of the fact that the impact of these new technologies may be on balance quite positive, but it will impact different communities and different parts of the workforce much more heavily than others. So thinking about how we not just make sure that we have the skills in our educational system, but also working on skill building and retraining for workers who are ultimately going to need to find new kinds of jobs has to be a huge priority in the years ahead. There's a lot of work that's going on in this space. The Commerce Department, we have our Skills for Business initiative, which is aimed at helping incentivize retraining and think about new approaches to it. White House has had the very successful Tech Hire initiative, really looking at how do we fill the hundreds of thousands, 600,000, 900,000 IT jobs that are currently unfilled in America. And that's not just about the big IT companies, right? And it's not just about Silicon Valley. This is about jobs everywhere. Every company today is a digital company in some way, and making sure that we have a workforce that can engage in those things and have the new skills they're going to need. And that includes thinking about different ways of measuring skills. It's not just about what you got your 4-year diploma in, college diploma in. Accelerators, boot camps, short-term badging of people so that we have new ways of measuring the skills that folks have that are going to be applicable in this new world. All of that is part and parcel. The Department of Labor is doing a lot of work on this, Department of Education. Part and parcel of this huge project we will now have in the coming years to deal with the workforce that's being dislocated.
Yeah, I can second both of those. I mean, I'm in a situation right now where I have an enormous number of unfilled recs for deep learning in particular. But one thing I've discovered is that there's actually, because it's such a new area, it doesn't take very long for somebody to become an expert in deep learning if they have the right background. But that background is really strong background in mathematics, in statistics, and in computer science. And I've been frustrated by the fact that I think the educational institutions, even the universities, have been very slow to pivot and recognize the huge demand for these fundamental skills, not the what I'll call almost trade skills of understanding deep learning, but the underlying fundamentals versus some fields of even science and engineering that are not as relevant as they once were. Even at large auto company is worried more about people that understand deep learning and software engineers than they are about mechanical engineers. They need a few people to design the chassis and the engines, but they need way more people to write the software and train the networks.
And they should. And the issue of practical skills is a really interesting one, right? I mean, whether we should be thinking about apprenticeship models and we've got a partnership with the Swiss and German governments to look at incentivizing those, or I visited an accelerator out in San Francisco a couple of months ago where they're doing these 3 or 6 month kind of retraining programs in data science where people come out, people who don't have a deep background in this come out with a very practical set of skills, and then of course it's up to industry to make sure that they can recognize that badge or that certificate as something that's valuable. But those models are going to be things we're going to need to be looking at.
I think there's an interesting paradox with AI as well, because even though AI is taking away some jobs, AI is also being helpful for retraining in the workforce. So there's a nice example of digital tutors being used. Department of Defense actually did a study of using AI-based digital tutors to teach new soldiers some skills. And they found that the digital tutoring approach was much more effective than their traditional approach of training. And so in an interesting, kind of paradox here, the AI can actually help us retrain if we take advantage of some of these digital tutoring technologies.
I think one thing that makes this difficult is we have this general notion that new jobs are going to be created and that some jobs are going to be replaced, and that every technological revolution up until now has had something like this. I mean, my advisor in college had worked as a computer at a time when that was a job that a human had, right? And that was a very highly skilled job that was replaced by what we now call computers. A lot of the jobs that we're concerned about being threatened now are things like taxi drivers, right? And so the notion that someone who is a taxi driver can be trained to be a deep learning scientist, I think there are certainly some numbers that will be able to, but that's going to require a lot of background training. So we have to think about what are some of the other skills that are not the production of AI, but that are complements to AI that can replace some of the jobs that might be lost.
Well, I think we may be running out of time. So I want to thank everyone. I want to thank our panelists for your expertise and wisdom. I want to thank our attendees for all the excellent questions that we got that I regret we didn't have time to get to. And certainly, I hope you enjoy the rest of the conference. Thank you very much.
Thank you.